Hi folks, in this tutorial we'll briefly explore how the works of the following scientists, Louis de Broglie, Erwin Schrödinger, and Werner Heisenberg have led to our current understanding of atomic orbitals. In the previous tutorial we did introduce the concept of atomic orbitals, but that was just to facilitate our understanding of quantum numbers. However, this tutorial describes how they have been derived and what are the other features associated with them. With the Louis de Broglie proposal that matter can displace wave-like properties, and which was proven experimentally to be so for the electron, Erwin Schrödinger, Austrian physicist, will come to the fore to address the concerns that relate to the electron's wave nature. In 1926, he would publish a complex wave equation, which will later be named after him. The solution to this equation, as it relates to the hydrogen atom, is called the wave function. It incorporated three of the four quantum numbers, n, l, and ml, and inserting certain values for these give a solution that describes the volume of space around the nucleus, or what is called an orbital. This model that uses waves to represent electrons is called a wave or the quantum mechanical model of the atom. If the values for n equals 1, l equals 0, and ml equals 0 are inserted into the wave function, an orbital with the following shape is produced. Here we see a spherically shaped orbital is produced. If n is equal to 2, and l is equal to 0, and ml is equal to 0, and these are also inserted into the wave function, an orbital that is spherical is produced, but it is bigger in size than this one here. So everything stays the same, l and ml stay the same, but the value for n changes, which means that is an orbital in the second shell. That is why now it appears as a sphere, but larger in size than the first one. If the values for n equals 2, l equals 1, and ml equals 0 are inserted into the wave function, an orbital with the following shape is produced, and that is a dumbbell-shaped orbital. However, if all these values remain the same, but you change n to 3, you get a same dumbbell-shaped orbital, but one that is bigger than that one there. If the values for n equals 3, l equals 2, ml equals 0, or negative 1, negative 2, positive 1, positive 2, are inserted into the wave function, orbitals with the following shapes are obtained. Here you're going to get a dumbbell-shaped orbital that is passing through this donut-like structure here, and four of them will be four lobe structures that are oriented in four different ways along the x, y, and z axis. Alright. The Heisenberg uncertainty principle. One of the problems with the wave theory of matter was that it does not say much about where the electron is found and how it behaves within an orbital. This problem was addressed by a student of Bohr, Werner Heisenberg, whose publication in 1927 included an equation that showed how it is not possible to know both the position of a particle x and its momentum with precision at the same time. According to his equation, for small particles such as an electron, neither its position nor its speed can be known with precision. An orbital is thus redefined as a volume of space around the nucleus where there is a probability of finding the electron. It is negative in nature and is thus characterized as a negative cloud. And of course, that volume of space will be characterized as a negative cloud. So, the orbitals produced have different shapes, sizes, and different orientations around the nucleus. You have orbitals that are called s orbitals, meaning sharp, and these orbitals are spherical in nature. You have orbitals that are called p orbitals, meaning principal, and these are dumbbell shaped. Then you have d orbitals, d meaning diffuse. You have 5 d orbitals, and one of them is like this, and 4 of them are 4 lobe structures, like we said, and they are aligned differently along the y, x, and z axis. And of course you have f orbitals, f meaning focal, and there are 7 types of those. We will not be examining those. This figure here has lots of condensed information about atomic orbitals. We look at this table here and gradually dissect all the information that is given. Here you see in the top row here you have the various shells, or we call energy levels, and beneath those are given their respective principal quantum numbers. K shell principal quantum number 1, L shell principal quantum number 2, M shell principal quantum number 3, and N shell principal quantum number n equals 4. It also shows how many electrons can be accommodated by each energy level, and how those values can be calculated using this formula here. If you insert a value for n here and you carry out this mathematical operation, you'll get these values here. You can see that the K shell, you have 2 electrons inside only, because n is equal to 1, and that works out to be equal to 2. In this shell here, you'll have maximum of 8 electrons. Put in n equals 2, it works out to give you 8. Doing the same thing for this one with principal quantum number equals 3 gives you 18 electrons, and that one here will give you 32 electrons. And of course we know that each orbital can only hold 2 electrons, so the number of orbitals in the K shell will be equal to 1. Here you have 8 electrons, you're going to have 4 orbitals, 18 electrons, 9 orbitals, 32 electrons, 16 orbitals. The number and types of orbitals within each shell, and also the way the electrons are spinning within these orbitals. So if we look at the K shell now, you can see it has one spherical orbital that is called the 1s orbital. The other shell has 2 types of orbitals. It has another s orbital that we call 2s in position but not number. This is called the 1s because it's in the first shell. This is called the 2s because it's in the second shell. And of course you'll have 3 of these dumbbell shaped orbitals that are called p orbitals. We call these 2 p orbitals because they're found in the second shell. And people are given these certain names. One of them is called the 2px orbital, 2py orbital, 2pz orbital, because of their orientation along the x, y, and z axes. In the third shell you have another s orbital. It's called the 3s orbital. So 1s, 2s, 3s in position, and you can see as you move outwards away from the nucleus, the orbitals are becoming bigger and bigger. And of course you have 3p orbitals. But this figure here, as we have alluded to before, shows how the 3p orbitals here are aligned along their axes here. This one we will call the 3py orbital because it's oriented along that axis here. This one we call the 3pz orbital because it's aligned along the z-axis, and this one here we call it 3px orbital because it is aligned on the x-axis there. So, and this one you have an s and 3 p's, and these will account for 8 electrons. But of course we know this shell has 18 electrons, so we need to account for the next 10 electrons, and that is where these 5 different d orbitals come in. You have 4 of these are 4-lobed in nature, and this one again we say is a dumbbell shaped one that's passing through a donut-like structure. And again, the way they're oriented along these axes, they're described as follows. This one is called the dxz orbital. This one is called the dyz orbital. This one is called the dxy orbital. This is called the dx squared minus y squared orbital. And of course this is a dz squared orbital. All because of how they are arranged along these axes. So this is the number and types of orbitals that are found in the various shells. Okay? First shell, only s orbital, second shell S and P orbitals, third shell S, P and D orbitals. Of course, we have the N shell here that will have a maximum of 32 electrons, and you're going to have 16 orbitals here. You're going to have a 4s orbital, 3 4p orbitals, 5 4d orbitals, and 7 f orbitals. Okay, I'm going to talk now about secondary quantum number, L, or sometimes it is called the angular quantum number. Look at some patterns here. All s orbitals, because they don't make an angle with respect to the axis, they have 0 secondary quantum numbers. The p orbitals will have a secondary quantum number of 1 to distinguish them from this s orbital here. Let us suppose that an orbital is from the second shell. It could be either an s or a p orbital. To distinguish the p from the s, we know s is 0, then p is 1. Something similar will happen in the third shell. This is the third shell here. The s orbital here will have a secondary quantum number of 0, but to distinguish the p's from that one, these will have a secondary quantum number of 1. But you're also having 5d orbitals in the third shell. So to distinguish the d orbitals from the s and the p orbitals, they're given a secondary quantum number of 2. So if someone says to you, an orbital has principal quantum number 3 and secondary quantum number 0, you're talking about this 3s orbital here. If they say an orbital has principal quantum number n equals 3 and L equals 1, you're talking about one of these 3 p orbitals. Again, if they say to you an orbital has principal quantum number n equals 3 and the secondary quantum number L equals 2, then you're talking about one of these 5d orbitals here. Okay, this needs a little bit of fixing. Don't worry, this is the y. It's just coming through here. That is secondary quantum number, and this is how we can use secondary quantum number to distinguish what type of orbitals you're talking about. Okay, then you have magnetic quantum number. All s orbitals will have 0 magnetic quantum number. Two things are common about s orbitals. They all have the same secondary quantum number of 0, and they all have the same magnetic quantum number of 0. So if someone says to you again, an orbital has n equals 2, L equals 1, it could be any one of these 3 2p orbitals here, okay? But to distinguish which one is lying on the x-axis and the y-axis and the z-axis, these magnetic quantum numbers are used. I do not know for sure which magnetic quantum number relates to each one of these orbitals here. So I have arbitrarily assigned the 2px1 to have a magnetic quantum number of -1, the 2py orbital to have a magnetic quantum number of +1, and the 2pz orbital to have a magnetic quantum number of 0. So let me ask you this question now. What 3 quantum numbers would this orbital have? First of all, it will have a principal quantum number of n equals 2 because it's in the second shell. It will have a secondary quantum number of L equals 1 to distinguish it from this s orbital here. And if we say that this one is related to this one here, it will have a magnetic quantum number ml of 0. Now if you go to the third shell, we know that the s is going to be 0, the p is going to have L equals 1, and again, like the 2p orbitals, we have to know which of the 3 we're talking about, and this is where these magnetic quantum numbers come in. Again, if we make the assumption here, like we did for this one, if I say to you that an orbital has principal quantum number n equals 3, L equals 1, I'm talking about a 3p orbital. But to know which one of the 3p orbitals I'm talking about, if we say ml is equal to positive 1, we're talking about this 3pz orbital. If I said that ml is equal to negative 1, we'll be talking about this 3px orbital. Alright? Same thing will happen for these d orbitals here. Of course, all these d orbitals will have n equals 3, L equals what? L must be equal to what now? L can be equal to 1. L must be equal to 2 to distinguish from these. So they all have a common n quantum number, 3. But they have different secondary quantum number to distinguish what type of orbitals they are, 0, 1, and then this must be 2. So the moment you hear n equals 3 and L equals 2, you're talking about a 3D orbital. Which one you're talking about specifically? We have now to give the magnetic quantum number, and because you have 5 of them, you have 5 different magnetic quantum numbers here. Negative 2, negative 1, 0, positive 1, and positive 2. And again, I have arbitrarily assigned some magnetic quantum numbers to these different d orbitals here. So let's say somebody says to you, okay, an orbital has a principal quantum number of 3. You're talking about the third shell electrons. It has a secondary quantum number of 2. It means you're talking about one of these 5d orbitals. How do I know which one I'm talking about? You have to look at the way they're oriented in space and the specific quantum number. So if I say ml is equal to negative 1, I'm talking about this d orbital here, dx orbital. Okay? If I say to you n equals 3, L equals 2, and ml equals positive 1, I'm talking about this orbital here. Okay? In each one of these orbitals here have 2 electrons. We can assign a positive half for the electron that's moving in the clockwise direction and a negative half for the one that's moving in the anti-clockwise direction. So let's give you another one. Let us say that an electron has a principal quantum number n equals 3. You're talking about an electron in the third shell. L equals 1. We are talking about an electron in one of these 3p orbitals here. ml equals a positive 1. I'm talking about an electron that's found inside this 3pz orbital here. And I say it is going clockwise direction. It will have a spin quantum number of a positive half. Alright, and like that, we can assign quantum numbers to any one of these orbitals here and the electrons that are found in them. So you can have another look at that. This gives you the shells there and the principal quantum number here. It gives the number of electrons in each of these orbitals here. That's found by using the formula 2n squared. It gives you a number of orbitals. It gives you the type of orbitals in each, type and number of orbitals in each. You can use now L quantum number to distinguish between S, P, and D, and you can then use magnetic quantum numbers to give you the way these orbitals here, except these S orbitals that don't make any angle with respect to the axes. I hope this tutorial is beneficial to you. Our next tutorial deals with energy level diagrams and electron configuration. Please don't forget to subscribe. Thank you.